Hey there. Today we are going to talk about the graphs of exponential functions. We've had a little bit of an introduction in the last sections to what an exponential function is, but now we want to start exploring what that graph looks like. So here are two versions of the graph depending on what the base is. If a base is greater than 1, we can see that I get an increasing function that's going up to the right. If b is between 0 and 1, so some fraction, then it's decreasing, going down to the right. Both of these functions we can see has a domain of everything from negative infinity to infinity. There's no value that you can't plug into this. The range, however, we can see they both kind of approach 0 as we go off to the right or left, depending on the value of b. But they approach 0 and never actually hit it. So the range goes from 0 to infinity, not including 0. And there is a y-intercept, an asymptote at y equals 0. The y-intercept for both of these is at 0, 1. If you think about it, if I plug in 0 for the exponent, I get a number to the 0 power. So I'm always going to get 1 there for the simplest version of this. These functions are one-to-one, which becomes important later when we start talking about inverses. And yeah, I think we covered everything on these graphs. So it's just good to be familiar with them, get an idea of what they look like. We're going to start translating them in a bit, so shifting them up and down or left and right. But this is what a basic function, just b to the x, looks like. All right, so let's practice with some graphing and finding some aspects of it. So here we want to graph the function f of x equals 4 times 6 to the x. And then we want to identify the domain, range, and asymptotes for it. So because these graphs are so distinctive, really you get the 1 point and you identify whether it's increasing or decreasing, and you can sketch the graph pretty quickly. So what I'm going to do to start out is just plug in 0 for x, find that y-intercept. So if I plug in f of 0, I get 4 times 6 to the 0. And so that 6 to the 0 is just 1. I get just 4. So I know that this graph intersects the y-axis at 4. The base of 6 is positive. This function is positive, so I know it's increasing to the right. Sorry, not positive. It's greater than 1. 6 is greater than 1, so I know it's increasing to the right. So already I can get a pretty good sketch of it that looks like this. And like I said, the domain is going to be everything for any exponential function. So negative infinity to infinity is the domain. And this one doesn't have any shifts to it. It's just, 4 times a number to the x. So its domain is going to be the same as the examples we saw, 0 to infinity. It approaches the x-axis at 0 there, but never actually hits it. So I still have a horizontal asymptote at y equals 0. Right, so some of these things like the range and the asymptote will start to change if we start adding and subtracting numbers to the basic version of the exponential function. So transformations can occur in a few different places. I can multiply by a. So I have a times b to the x here. If I add a number to the exponent, to the x in the exponent, then that will cause a horizontal shift. If I add a number to the end of the function, that will cause a vertical shift, so that it will go up or down by d. The number a out front, if I take the absolute value of it, if it's greater than 1, then that will stretch the function vertically by a factor of a. Like we saw in that last one, it was pretty steep. It was stretched vertically. If a is less than 1, after I take its absolute value, then it's compressed vertically. It's squished and kind of gets, goes out fatter. If a is less than 1, then the graph will be reflected about the x-axis. So it'll be flipped down about the x-axis. If the exponent is negative, then it will be flipped about the y-axis. Okay, so think about it rotating about the y-axis. So let's look at some examples with this, where we take that last function, 4 times 6 to the x, and we mess with it a little bit more. So I'm going to graph each one of these translations. Remember, our original graph looked like this. It went through the 0.04 and is increasing to the right. So if I just subtract a 2 to the end of the function, so 4 times 6 to the x minus 2, that shifts everything down 2 because it's negative. So now instead of having y-intercept at 0, 4, it has a y-intercept at 0, 2. And instead of having a horizontal asymptote at 0, it has a horizontal asymptote at -2. So it just takes everything and shifts it down. For part B here, we have 4 times 6 to the -x. So that's a reflection. And it reflects it about the y-axis. So everything gets flipped. The y-intercept doesn't change. The asymptote doesn't change. Just everything else flips sides. And then the last one, if I do 4 times 6 to the x plus 1, so that is a horizontal shift. And these do, if you recall when we did translations, it goes the opposite direction of you would expect with a horizontal translation. So if it's +1, I go to the left one. If it had been -1, it would have gone to the right one. So that's just some examples with transformations. With graphing technology like Desmos, you can play around with these pretty easily to get the feel for how a transformation will work. The other thing we want to be able to do with these exponential functions and their graphs is come up with an equation. So we want to write the equation of an exponential function of the form f of x equals a times b to the x plus d that goes through the points 0, -1, and -1, -11, and has an asymptote at y equals 1. Okay, so I know there's no horizontal translation because the general form didn't have a number adding to x in the exponent. So I don't have to worry about that part. But there is a plus d, and I can see that also the asymptote is not the usual y equals 0, it's y equals 1. So just that piece alone tells me what d is. I know that this has been shifted up 1 because the asymptote is 1 higher than it normally would be. So I know that already the function looks like f of x equals a times b to the x plus 1. So that took one of the unknowns and took care of that, the d. Now I just have to find a and b using the other 2 points they gave me. So just like in the last section, I want to start by using that y-intercept, 0, -1, plugging it in. So I plug in -1 for y and 0 for x, and I get -1 equals a times b to the 0 plus 1. B to the 0 is just 1, so this simplifies to -2 equals a plus 1. And if I subtract that 1 over, I get a equals -2. So down, I've got the d, I've got the a. Last thing to come up with is the b. So far the function looks like -2 b to the x plus 1. So I got 1 point I haven't used yet. I'm going to plug in -1, -11. So -11 equals -2 times b to the -1 plus 1. If I subtract 1 over, I get a -12 equals -2b to the -1. And then I'm going to divide by -2. And at the same time, I'm going to write that b to the -1 as 1 over b. For me, it just makes it a little easier to solve it this way. So I have 6 equals 1 over b. And there's a variety of ways you could solve this. The fastest way is just to think of that 6 as being 6 over 1. And well, if 6 over 1 equals 1 over b, then if I flip both fractions, they'll still be equal. So b equals 1 over 6. So I've got my equation, f of x equals -2 times 1/6 to the x plus 1.